Okay, so today's lesson will be over statistical models. I'm going to go ahead and show you the things that I have here. Remember to go to Edmentum, log in, go to the mastery test that says statistical models. So we have the guided notes, which again, all of these will be linked in the email that I will send today. When I upload this video at the same time, I will also email out this paperwork. We have actually 4 pages, but it is front and back. So it's this page, the back of it, this one, and then the back of it, the last page will say summary. Again, when it gets emailed to you, it's in PDF form and it's all just on single pages. So it just depends on how you print it out. The next thing that you'll have is probability review. So it'll go over some things that were not included in the tutorial that I'm guessing will show up in the mastery test. And that's why they put it on there. The next thing is, I'll include it again in the email, but these are the same terms that we used last time. So if you already printed these out, again, these are all of the vocabulary words for Algebra 2 Semester B, which is what we're doing on Edmentum the whole time. So these words have already been printed out or sent out. You don't have to reprint them if you already printed them. So I'm going to set these aside. I only use them to put definitions into the paper. Okay. So we're going to start with this and then we'll end with the review. And I'll have to remember to push this up when it gets to here. I do think it's better if I record this sideways. It's a little bit more zoomed in, and I think it works better for like the picture quality or video quality in this case. Okay, so once again, I got these from the tutorial videos, and what I'm doing is I've already got these filled out. So I'm gonna go through, just kind of give you some hints over what was in the videos that I noticed, made some remarks, and then again, filling in the blanks as we go. It might help you to have these blank beside you and try to do the tutorial video and try to fill in the things on your own. It might be helpful for you to just watch my video and fill in the whole thing and then use the filled in information to help you and rewatch the tutorial and then take the mastery test. I know in Algebra 2 I've noticed that there is a practice activity or a practice test. I can't remember how it's labeled. So if you do need help with that, or if you would like me to upload videos of the practice one, I can. The only thing I can't help you with is, again, the mastery test, because that's what gives you a pass or fail for that lesson. And again, the aim is just to get a 70 or higher. So if you make a 70 or higher, you pass. So it's pass fail. So it's not like if you made an 80, I'm going to put an 80 in the grade book. So I won't even be messing with the grades until we return. God willing that we return soon. So right now, do not worry too much about the numerical grade, just as long as it's higher than a 70. Okay, so let's get started. Statistical models. So we're going to be talking about what types of statistics will be used so we can predict outcomes. It's a little bit misleading when it says models, because typically we think of models as like bar graphs and pie graphs and things like that. You are going to run into that, but not for this lesson. Okay. So just to review the things that are already filled in: statistics, a process for making inferences about population parameters based on a random sample from that population. And then population, if you remember, is the overall group from which data is sampled. So again, what does it mean for a population? It's not necessarily just people. It's anything that you are studying data on that you can take and make a smaller chunk of. So population in general is a big amount, whereas the sample that you take out will be a smaller amount. Inference, a conclusion about a population based on statistics of a random sample from that population. So again, it's when we take data and we make a prediction from there. Statistical models, so this is what we'll be talking about mainly here. It's a mathematical representation And again, these words are on the vocabulary list, so if you just want to copy and paste, if you're just using the computer and then print them out, that's fine. If you just want to shorthand it, that's okay, but I am getting these word for word from the definitions that were provided in the glossary. So it's a mathematical representation of data that can be used to make inferences, which we already discussed what that is, or make predictions with the use of probability. Okay, so probability is actually the main key word there. We're going to be talking a lot about probability, in particular two types, theoretical and experimental. And it's kind of in the wording. Theoretical is something that you think is going to happen. Experimental is it's proven. You experiment over and over again until you see the probability. So theoretical probability is the likeliness of an event to occur based on all possible outcomes. Which we'll talk more about like in the actual work that we'll be doing here, what that is. Experimental is the ratio of the number of times, and ratio is a fancy way of saying it's going to be a fraction, which is another way of saying that you're going to divide something. The ratio of the number of times an event occurs to the number of trials performed. And again, that's just a fancy way of saying that you're actually going to experiment. So trials is the experiment. You're actually going to go through there and you're going to test it over and over again. Okay, so again, we're going to go a little bit faster in this video. The other one was a little bit longer and I shouldn't have to explain as much anymore. And feel free to pause it if you need to, because I know some people learn a little bit slower than others, and for others, going fast is just fine. So you have the benefit of rewinding it if you need to and pausing it if you need to. So hopefully it's not so bad. In this lesson, you will compare statistical models with experimental and observational data. Okay, and again, this all comes from the tutorial. So from this star on forward, basically I hit play on the tutorial and that's how I'm getting all this information. Statistics is the science of generalizing about a larger population based on the information obtained from a smaller sample, which was what we discussed before. So you can't test the whole population, you only test a sample and then you move on from there. A statistical model is a mathematical tool we can use to make a generalization from data. We can use these models to make further predictions and inferences about what might happen in a scenario. To examine how we can use statistical models to predict the likeliness of outcomes, consider the following situation. Okay, just so you know, this point forward, this is the lesson activity. So if you skip the lesson activity, these next few parts of this worksheet are the lesson activity. This is what it says in the lesson activity. A poll is taken at a concession stand to discover the customer's favorite item to buy. The results are displayed in the table. So here's the results. The situation can be approximated by a model of rolling a die. Can be approximately modeled by rolling a die. So what they're trying to say is when you're going to make an experiment or make an inference, sometimes you don't have the ability to go back to a concession stand and count how many people pick pizza, how many people pick popcorn, hot dogs, etc. So instead, you represent it with something else. So that's what we're trying to do. In this case, they want to represent it with the outcome of rolling a die. And a die is just one of the dice. Dice is plural, so one die has 6 sides, and that's what we're talking about. Okay, let's keep in mind these numbers. We're trying to see from a die, how can we get these percents to show up? And that's what we're going to see on the back. So they've actually done that for us. So let's go to the back, or in this case, the next page. Okay, if we want to model the situation by rolling a die, let's first examine the probability associated with getting a certain roll with a die. Since there are 6 sides, there is a 1/6 or approximately 16.7% probability of any given number being rolled. So just to review, how do you change this fraction into a decimal? You divide 1 by 6, and then you get 0.16666, like it keeps going. We round that to 167, and then you move the decimal over twice. So that's how you get that percent. Okay, so that would be something you would do on a normal calculator. The probability that the outcome is greater than 3. So let's think about it on a die. What numbers are greater than 3? 4, 5, 6, and then after that you stop because there isn't a 7 or an 8 or so forth on a die. So that's 1, 2, 3 numbers. So there's 3 out of 6 chances of getting a 4, 5, or 6. Well, that's going to reduce to 1/2, which is another way of saying 0.5, which again is 50%. That's very close to 49.7. If you remember, that was the first number we had here. Okay? The probability that the outcome will be a 2 or a 3. So if it's either a 2 or a 3, that's 2 times, so that's 2 out of 6. That reduces to 1/3, which is another way of saying a third, which is 0.3 repeating. Again, we chop it off, we round it to 0.33, and we move the decimal twice, and we get 33%. That's really close to 33.4, which again is one of the percents we have on the front. This one was for popcorn. This one was for pizza. And lastly, the probability that the outcome will be a 1. Well, there's only one chance when you roll it that it's going to be a 1, so it's going to be 1 out of 6. Again, here's the decimal. We move the decimal over twice. That's our percent, and it's really close to this one, which was hot dogs, just so we don't have to keep flipping back over. Okay, so what this is saying, and after we get done with this, this is the end of the activity. So I'm going to put end activity here. Okay, so what this is saying is, instead of going and asking, what would you like, a hot dog, popcorn, or pizza, and keep going, what we could do is we could take a deck of cards, or sorry, not deck of cards, we could take a die and we could roll it, and then if we get a 4, it's going to be popcorn. We roll it again. If we get a 2, then it's going to be pizza. We roll it again. If we get 1, then it's hot dogs. And then that could represent that percent that we're getting. Again, this is just representing that. Instead of us having to go and actually do the experiment, our experiment would be the die. Another way to think about it is if you actually took the physical die, and like on the one that has a 1, it's this one, we write the word hot dog. And then the one that has 2, we write the word pizza, and so forth. And then that way, whenever you roll it, that's what it's representing. Okay, so now we're going to keep going in the tutorial. Models use probability to make predictions, but sometimes data will generate a probability that is different from the model. This is the difference between theoretical and experimental probability. So this is the big thing that we need to take away from today's lesson. What is the difference between theoretical and experimental? I'll kind of summarize it at the end, but hopefully you get it after we go over a few things. Theoretical probability provides an understanding of what is likely to occur with a lot of data over time. However, theoretical probability may not be a good predictor of things that offer little data. So you could have just a few points of data, take that and make a theoretical probability out of it, which would be a prediction. But if it's very little data, the chances of that probability being exactly correct is probably going to be very slim. The more data you have over a longer period of time, that theoretical probability makes sense. Basically what you're doing is you're looking at the data that has already been established, whether it be the day before, over the past year, over the past 5 years, and so forth, and you make a prediction, an inference over what's going to happen based off of something that you've already reported in the past. So here's an example of theoretical probability of drawing a red king. There are two, so hopefully you're familiar with a deck of cards. In a normal deck of cards, there's 52 cards. You take out the jokers and any extra cards, and you have just the face cards and the numbers and the aces, and there's 52 cards in a standard deck. There's only 2 red kings. The other 2 kings are black. So there's 2 red kings, and they want to know what's the probability of drawing one of those 2 red kings. This is how you get that. Just to put above this, it should have been in the tutorial, but this is the way you write it. P stands for probability. Event is whatever you're trying to get. So in this case, we're trying to get a red king, so that's why we write that there. Is equal to number of outcomes meet condition over the number of possible outcomes. Okay, so this is a fancy way of saying take the only amount of red cards that we have that are kings, put that on top. Put the total amount of cards that we have, put that on the bottom. So that's how we get this next one over here. We have the number 2 over 52. We can reduce that and change it into a decimal. Basically, I'm going to write out here, divide 2 by 52. So all I did in my calculator was 2 divided by 52. That gave me 0.038, and it kept going. I moved my decimal twice, and I get 3.8%. So that's my math for it. Okay, so basically what I'm saying is this is the chance that I'm going to get of getting a red card. I haven't actually drawn the card. I just said, based off of the fact that there's only 2 cards that are red and king, and there's a total of 52, if I divide them, I have a 3.8% chance of getting a card that is a red king. It's a hypothesis, it's an inference, that's all it is. But when you actually sit there and draw a card until you get the 2 number of kings that you need, and then you record the amount of percents it was, that's whenever it becomes experimental data, an experimental probability. So when you're just thinking it's going to be this, that's when it's theoretical. So down here, when we collect data in a study, it's empirical data. This data is used to develop an experimental probability. So there's that word. Experimental probability is the ratio, which again is the fancy way of saying fraction, which just means to divide, of outcomes that meet the condition to the total number of outcomes observed. So the key word is observed. That means you actually did the experiment. You actually went through and took a card out every time and then counted how many times you did that to get your percent. So this one is written this way. P, and then the event that you want to happen, is equal to the number of actual outcomes that meet condition over the total number of actual outcomes. So that's not saying that it's the full deck. It's saying how many total cards I had to draw before I got those two red face cards. Might not be the whole thing. Okay, so move on to the third page. And just so you know, this is once again a lesson activity. So if you skip that, these next few ones won't make sense because they weren't in just the tutorial. And this is where the activity ends. Okay, this one's actually not so bad. I think it's actually pretty simple to understand. So let's go over that very quickly. Let's compare theoretical and experimental probabilities with a real-world context. A traffic engineer finds that a traffic pattern at a particular stoplight can be modeled by spinning a spinner with 3 equal sections labeled as left, right, and straight. So those are the options you have when you get to that light. You can either go left, right, or straight. Based on this model, the theoretical probability that a car stopping at the light will go straight is, well, there's 3 outcomes. So it's going to be 3 on the bottom. And I want to know if I pick straight, that's going to be 1 out of the 3 choices. So straight is 1 out of the 3 choices. So this is a theoretical probability. We're not sitting there and actually testing out how many cars go straight. Which they don't ask you, but that's about 33%. I took 1 and I divided it by 3, and that's how I get that number. Okay, so now an engineer monitors the intersection and records the data in the table. So now he's actually recording the data. This is now turning into not theoretical, but an experimental, because now he's actually going to sit there and record the data. If we are right, there should be 33% of these cars that went straight. So let's see that. We can find the experimental probability that a car will go straight through the section based on the data that we collect. Okay, so let's look at how many went straight. So number 1 went straight, number 4, number 6, and number 9. So 4 out of 10 cars went straight. That reduces to 2 over 5. And then when we divide them, that's about 40% of the cars. So now we need to compare these. I think they ask you that in the little activity. Were they the same? No. Are they fairly close or not? That's a 7% difference. With it being cars and just to know if they go straight or not, 7% might not be that much. But if it's money, if it's calculations of how much food do I need to make it for the day, 7% might be enough to, miscalculate your amount of money that you make, the amount of hot dogs that you buy, things like that. So I would say they're not close enough for what I would like. Maybe 38, 39%, and 40, that would be a good amount to be. So the question is, why don't they match sometimes? And that's what we're going to figure out in the next sections. Okay, so that's the end of the activity, and now we start back at the tutorial. Sometimes in a statistical model, the theoretical probability doesn't match the empirical data or the experimental probability. That comes from it. When this is the case, it could mean one of 2 things. So these are the 2 things that could have happened to our data here above, or in any other situation. There isn't enough empirical data to show the pattern. This is known as the law of large numbers. Or the model needs to be adjusted or improved. So if we go back to the one that we just did with the cars, I do think that maybe there just wasn't enough cars. If they had done it the whole day and recorded how many cars, not just 10, if they had done at least 100 cars and reported what they did they either go straight, right, or left, we might have gotten closer to that 33%. Now, what factors could also play into this? Well, what if you're at a stop where the main road is straight and the 2 side roads where you go left or you go right are dead end roads, or roads that lead to maybe like just a housing unit? That's going to play a part in the fact that you're going to have more people drive straight, and this 1/3 is no longer relevant. It's going to be a higher number that would go straight. Okay, so again, that's just something that could happen. Either we need to take more data in, or we need to improve the basis of our data. Okay, so now let's compare empirical results from the experiments with observations from theoretical data and analyze the models. So this is once again another lesson activity. And if you skip it, you're not going to know where this came from. Okay, and just so you know, this is not our Central High School. This was just the name they used. Okay, Central High School is curious about how many 9th grade students in the district participate in band, choir, and athletics. Based on previous years, the statistics class came up with the model that shows 62% of 9th grade students who participate in extracurricular activities will be in athletics. The data collected from this year is shown in the table. So let's move to the table. This is the actual numbers from this year. The 62% was based on previous years. So this is theoretical. This is what we think will happen. This will be the amount of kids that if we were to collect data on that would be participating in athletics. But this is just an inference, it's a guess. So the theoretical probability that the 9th grader involved in extracurricular activities is involved in athletics is 62%. And again, that came from the thing that we had in the front. Okay, now here's the experimental probability. We're actually going to take these numbers here. We're actually only interested in two numbers, the athletics and the total. And we're going to see if 62% is correct. The experimental probability that a 9th grader involved in extracurricular activities is involved in athletics at each school can be determined by doing the following. Take the number of athletics, 91, and divide it by the total number, 150. In Central High School, we will do the same thing. We're going to take 40, and this was Valley High School, so that's how I got that number. This is Central High School, and the last one will be Logan High School. So in Central High School, 45 out of 92, and then Logan High, 64 out of 103. We take and we divide all these numbers, and they do want us to round, because I looked at the key, they want us to round to like the nearest whole number, so that would be 61%. This one would be 49%, and this last one would be 62%. Okay, so now we need to figure out, are these values what we predicted? So for Valley High, was it 62%? Nope. Nope. For this one it was. So not valid for Valley High, not valid for Central High, but it was valid for Logan. Now, this one's just off by 1%. I would give it to Valley High. I feel like our prediction was spot on for this one. On this one, it was off by 1%. Granted, we did round up when I got this percent, but it's not off by a lot. 49 is way off. So here is the question in the summary. And it asks you that on the activity as well. So this is the end of the activity, and then you keep going. It says, when there's a large difference between theoretical and experimental probability, what might be the cause of it? So the reason why there's a difference is because theoretical is just a prediction from previous data, whereas experimental is actual data collected to get probability. So that's where you get that difference. Now, when there's a large difference, that's when we have those two things that could happen. So you could go back and put that in the summary. My biggest thing from that is, like, for example, the schools. There's other factors that sometimes come into play. So like, let's say Valley High, Central High, and Logan High. In this activity, Central High School was the one with the smallest number of people who do extracurriculars. There might be a reason for that. Maybe they have a very bad basketball team or football team, and that's why less kids participate in athletics. Maybe they have just less enthusiasm into extracurricular activities. The more people you have, the more that are involved, something like that. If it's way off, remember you're supposed to either collect more data because maybe it's got a small number and you need a large number, or you need to adjust the way that you're asking the information because sometimes it makes it skewed, it makes it biased. Okay, so that is the end of the lesson. You could try to go from there and take the mastery test or the practice test and see how you do. The last thing I'm going to show you guys is the probability review. There's not a lot. You can kind of read through it. There's nothing really that I have to go over except for one thing that was not talked about in the tutorial at all, and that is the complement of an event. The complement of an event is just saying the opposite of the event. So it is denoted with a special mark. It's got an A with like an exponent and it's called a C. So this is read the complement of the probability of A. And all you do is you actually find the probability of whatever you're trying to find, and then you do 1 minus that. That's all you do. So to show an example of that, there is one down here. Suppose we roll a 6-sided die. The sample space of this experiment are the numbers that we can roll. The numbers we can roll are 1, 2, 3, 4, and 5, and 6. This means that there are a total of 6 possibilities. So that's going to be the number that goes on the bottom. And then now we're going to say that our event A is what happens if we roll a 5. What's the probability of that? So that's pretty simple. How many times could a 5 happen when you roll it? Just once, right? So the probability of rolling a 5 is 1 out of 6. Because there's 6 total, and that's how many times I could roll a 5 in one roll. So that is this number right here, 1, 6. The complement of that is actually very simple. You just do 1 minus 1, 6, which is equal to 5 over 6. Another way you could have figured this out is the complement is what are the probabilities of not getting a 5. So if you get a 1, a 2, a 3, 4, or a 6, then that's the complement. Well, there's 1, 2, 3, 4, 5 ways you could not get a 5. And then there's still 6 total. So that's how you get 5 over 6. Okay. So again, go over that, try it, see what you can do. And I will email this as soon as I can get this uploaded. And again, it'll include everything. I'll include the glossary again, even though you do not have to print it out again if you already printed it out before. And if you have it saved, you don't have to save it again. Okay, I will see you guys in the next video.